Okay, this is part 2 of the opening lectures on sound. Okay, next let's cover loudness. Okay, the word loudness is a physiological term. It's once again used to describe our senses. However, the corresponding physical quantity is a quantity that we haven't seen in class as of yet. Let me go ahead and introduce it here. It's what is called intensity. Okay, first of all, the definition of intensity, which is referred to as I, it's equal to power divided by area. Recall that power is energy per time. It's measured in terms of watts, whereas area would be measured, for example, in terms of meters squared. So the units of intensity are watts per meter squared. Okay, there's 2 ways to think of intensity. The first way of thinking of it is in terms of the production of sound, and then secondly in terms of receiving the sound or hearing the sound. So let me describe to you first of all intensity in the context of the production of sound. Okay, so for example, let's say that right here we have a source of sound, and that source of sound is emitting a constant frequency. Just think of it as my voice just going, like so. Okay, now it costs me a certain amount of energy per second to produce that sound. There is then therefore a power output associated with that source. We refer to this as P source. Okay, and then propagating outwards from the source are spherical wavefronts. For example, like so. Here's a spherical wavefront, and there's a radius r associated with that spherical sound wave. This then means that the area over which this energy is spreading is the increasingly larger and larger surface area of a sphere. And recall that the geometrical formula for the surface area of a sphere is 4 pi r squared. So then therefore the intensity of the sound at this location is equal to the power output of the source divided by the surface area of the sphere, which is 4 pi r squared. So notice that intensity obeys an inverse square law, just like, for example, Newtonian gravitation does. The reason for this is because we live in a 3-dimensional universe, and the energy in this case is spreading out over the increasingly larger and larger surface area of a sphere. Okay, recall the basics as to how an inverse square law works. Let's say, for example, that we double the distance away from the source. Then, therefore, the intensity is 1 over 2 squared, or 1/4 of its original value. If we triple the distance from the source, then the intensity is 1 over 3 squared, or 1/9 of its original value, and so on and so on. So the intensity of a sound wave drops off, if you will, in accordance with an inverse square law. Okay, now that's one way of thinking of intensity, that is in terms of the production of sound. You could also think of it in terms of receiving the sound. So imagine, for example, that you're standing right here, and there is a cross-sectional area associated with your ear. That would be then, for example, your eardrums area, and let's just refer to that as A. So in terms of receiving the sound, you can then think of intensity as the amount of energy per second that is passing through your eardrum, that is passing through the area A. So the same value of intensity as it was before, but now in terms of receiving the sound, can be thought of as the amount of energy that is received per second. We usually write this as P receive, and then divided by the area through which that energy is passing. In this case, for example, the area of your eardrum. So there's 2 ways to think of intensity in terms of the production of sound and in terms of receiving it. Okay? Okay, now how does intensity correspond to loudness? Okay, first of all, the softest audible sound, the intensity associated with it is next to nothing. The softest audible sound is referred to as I naught, and it's equal to literally a trillionth of a watt per meter squared. So 1 times 10 to the minus 12 is a trillionth of a watt per meter squared. So what would the intensity I naught, the softest audible sound like? Well, it may sound, for example, say something. Now, I doubt whether or not my microphone was able to pick that whisper up as I was whispering. However, the way that I normally demonstrate this is to do exactly what I just did right next to a student sitting in the front row. That student could probably hear a couple of the words that I was saying, but certainly on the other side of the room, another student would not be able to hear me in accordance with the inverse square law. So in other words, the intensity of the sound wave by the time it reaches the other side of the room is well below this value here. Okay, now what we perceive to be a doubling in loudness corresponds to an increase in intensity by a factor of 10. What we perceive to be a doubling in loudness corresponds to an increase in intensity by a factor of 10. So 1 times 10 to the minus 11 watts per meter squared, we would then perceive that as twice as loud as this value here. 1 times 10 to the minus 10 watts per meter squared, we would perceive that as twice as loud as 1 times 10 to the minus 11th. We would perceive it as 4 times as loud as 1 times 10 to the minus 12th, and so on and so on and so on. Because of this, then, it makes sense for us to define a scale associated with loudness that is based upon a base 10 logarithm. It's a logarithmic scale, and this is the decibel scale. Okay, the decibel scale is just a definition, nothing more, and it's a base 10 logarithmic scale that we then use to describe loudness. Okay, first of all, the scale itself is referred to with the Greek letter beta, and this value here is sometimes referred to as the intensity level. I know that that's a little bit confusing, but this is referred to sometimes as the intensity level, the amount of decibels. Okay, by definition, it's equal to the following quantity. This expression here, and let me now explain what the various terms are. First of all, as you'll see in my first numerical example in just a few minutes, the scale itself is actually defined in terms of I naught, the softest audible sound. And then I is the intensity of the sound that you're hearing, the amount of decibels, the intensity level, that's then the quantity beta. This quantity right here by itself, just the logarithm, this right here is referred to as a bell. It's usually a small number. So then therefore what we do is we just simply multiply it by 10 to then end up with what are referred to as decibels. So then therefore we end up with whole numbers to work with. The Richter scale, by the way, for seismic waves works roughly the same way. It's once again a base 10 logarithmic scale. So if you're talking about a Richter scale 6, for example, this then means that that seismic wave is 10 times as intense as a Richter scale 5. It's 100 times as intense, for example, that is a Richter scale 7, would be 100 times as intense as a Richter scale 5, and so on and so on. So on the Richter scale, a increase in intensity by a factor of 10, that then corresponds to one value on the Richter scale itself. The decibel scale works in much the same way. Okay, now the easiest way to see how the scale works is just to take a look at a couple of examples. So at this point right now, go ahead and copy down the first of today's lecture examples in your notes. It is as follows. Find the intensity of the following intensity levels, 0, 10, 20, and then a couple of fun terms that we'll work with here in a few minutes, 120 and 180 decibels expressively. Okay, so let's go ahead and take a look at that problem. First of all, I naught, once again, is 1 times 10 to the minus 12 watts per meter squared, and then here's the scale itself. Okay, now in part A of the problem, we're just simply setting the amount of decibels here equal to 0. So that's here on the left-hand side. Like so, and now we're just going to solve for I, the intensity. So just cancel out the 10 here in this opening example, and then to get rid of a base 10 logarithm, we do the following. 10 to the 0th on the left-hand side of the expression equals 10 to the log of the stuff. 10 to the log of the stuff is just the stuff, that is, it's the parentheses, like so. 10 to the 0th is 1, so then therefore the intensity I is equal to the intensity I naught, 1 times 10 to the minus 12 watts per meter squared. So as I said earlier, the decibel scale is basically defined in terms of the softest audible sound that's being illustrated here in part A of the example. Okay, now in part B, now we'll set beta equal to 10 decibels. And by the way, the word decibel is not a unit of measurement. It's instead just a name that is given to this quantity. This quantity actually has no units, it's dimensionless. So this right here is just a name, it's not a unit. So now what I do here is just on the left-hand side, set beta equal to 10. Like so, and then we just once again solve for I. So cancel out a 10 in this case, and that then becomes a 1 on the left-hand side, and now get rid of the base 10 logarithm. So 10 to the first power equals then I over I naught, and then solve for I. So I is going to be 10 to the first times I naught, which is 1 times 10 to the minus 11 watts per meter squared, which is perceived as twice as loud as what we did earlier in part A of the problem, when the intensity was 1 times 10 to the minus 12 watts per meter squared. So then therefore we perceive this to be a doubling in loudness, and notice that that corresponds to an increase in the amount of decibels, the intensity level, by 10. So in other words, 10 decibels is twice as loud as 0 decibels. As you'll see in part C in just a few moments, 20 decibels is twice as loud as 10 decibels. Therefore, it's 4 times as loud as 0 decibels, and so on and so on. So every time that you increase in the intensity level by 10 decibels, that corresponds to an increase in the intensity by a factor of 10. This then means that we perceive it to be a doubling in loudness. That's how the scale works. And as I said earlier, the Richter scale works much the same way in the context of seismic waves. Okay, so let's take a look at C here. As I do, you'll get the idea of this pattern I just mentioned. So now we set beta equal to 20 decibels. Like so, and now we just solve for I. So do a little bit of canceling here, and that becomes 10. And then get rid of the logarithm, so 10 squared equals then I over I naught. So I is equal to 10 squared times I naught. So 100 times I naught is 1 times 10 to the minus 10 watts per meter squared. So this is 10 times as intense as 1 times 10 to the minus 11 watts per meter squared. Therefore, 20 decibels is twice as loud as 10 decibels. Normal conversational voice, by the way, when you're just standing next to somebody and talking in your normal voice, that's usually around 30 odd decibels or so. When I lecture, of course, I am speaking a little bit more forcefully, and I'm speaking a little bit more loudly, so then therefore the amount of decibels associated with my voice as I lecture is maybe upwards of maybe almost 40 decibels, something like that. Okay, now a couple of fun numbers here in parts D and E. So part D is 120 decibels. You may recognize this number, and the reason for that is because of the intensity of the sound that it corresponds to. Let's go ahead and calculate that intensity before I describe its meaning. All right, so I'm going to go ahead and set beta equal to 120. Like so, and then I just once again solve for I naught. So do a little bit of canceling, and this becomes a 12. Okay, get rid of the base 10 logarithm, so 10 to the 12th then equals I over I naught, and then solve for I. Like so. So this is a trillion multiplied by a trillionth. This then gives us 1 watt per meter squared. This is the point where sound starts to become painful. This is referred to as the threshold of pain. So for those of you that have been to an indoor concert, for example, and of course I've been to many, If you happen to stand right next to the PA system or the speaker in an indoor concert, you're basically right at 120 decibels. You're right at the threshold of pain. You can know this ahead of time, for example, because how many of you have ever felt your clothes ruffle a little bit if you're standing next to a speaker and it's particularly loud in an indoor concert? Well, you're receiving a rather significant amount of energy when you do. In this case, it's about 1 watt per meter squared, and then therefore this is the point where the sound itself becomes painful. If you've ever suffered from muffled hearing or kind of like a high-pitched sound in your ears, perhaps for a couple of hours or perhaps the next day after a concert, well, congratulations, you have actually damaged your hearing. You are suffering from what is referred to as tinnitus. It's also sometimes called tinnitus. So it's kind of like skinning your knee, however. Your body, of course, has the ability to heal itself, and then therefore after a day or so, your eardrum then heals. However, if you repeatedly expose yourself to really loud sounds, as I have done over the years, then at this point your body's ability to heal itself begins to degrade, and then you can actually damage your hearing. There are a number of famous examples of musicians that have over the years have damaged their hearing to the point where they're actually legally deaf. You want to make sure that you protect your hearing. The easiest way to protect your hearing, by the way, is just to simply move a little bit backwards from the speaker itself. If you do, you're taking advantage of the inverse square law, and then therefore, of course, the sound is not going to be quite as intense. This is a little bit difficult in an indoor concert venue, however, because you have sound reflecting off the ceiling and the walls and so on and so forth. It's much easier to do at an outdoor concert because in an outdoor concert, all the sound just propagates outwards like so as a spherical sound wave, and then therefore it drops off pretty quickly in terms of its intensity as you move away from the speaker in accordance with the inverse square law. But you definitely, of course, want to protect your hearing by using, for example, some ear protection of some manner. I suggest, by the way, buying these little foam earplugs that you can get at CVS Pharmacy, for example. You could buy a pack of like 50 of them for like a couple of bucks. The easiest way to protect yourself and still enjoy the music that you're there to listen to is to take those foam earplugs and just kind of lightly place them in your ear canal. You don't have to jam them all the way in, but just kind of lightly place them in your ear canal so that you could still hear all the frequencies of the sound that you're there to enjoy, but still it will then lower the intensity below the threshold of pain. So you want to take steps to protect yourself, and that's the easiest way to do so. Okay, and then part E. Part E is another fun number, if you will. Okay, first of all, in part E, the level of intensity, the intensity level, is 180 decibels. When you get to this point here, we no longer really begin to think of it as sound. Instead, it's just this enormous pressure wave that is propagating through the air. Okay, let's calculate the intensity. All right, so going up to the scale and setting the left-hand side here equal to 180, let's now go ahead and solve for I. So do some canceling, and this becomes an 18. Get rid of the logarithm, so 10 to the 18th equals I over I naught, and then solve for I. Like so. 10 to the 18th multiplied by 10 to the minus 12 is 10 to the 6. 1 times 10 to the 6 watts per meter squared, 1,000,000 watts per meter squared. It's at this point here where the sound wave is so intense, the amplitude of that wave is so big, the energy that's present there is so large that it's literally going to rip your body apart. This is referred to as the threshold of death. So it's at that level then, the threshold of death, that we no longer really refer to it as sound because the sound wave itself is so intense and it basically would blow your body apart. So what would the threshold of death be? Well, imagine standing next to a bomb and the bomb goes off. Okay, the shrapnel doesn't necessarily kill you, but the pressure wave does. It basically blows your body apart, and that's why this is referred to as the threshold of death. Okay, here is, however, a sound that is common in between the threshold of pain and the threshold of death, and this would be around 140 decibels. This is typical of what you would hear if you were standing next to a jet engine, for example, at full throttle. So that's why you see airport workers on the tarmac, for example, wearing those enormous earmuffs. Those are there, of course, to protect their ears from those intense sounds associated with jet engines at full throttle. If you stood next to a jet engine at full throttle without any ear protection whatsoever, you're going to suffer permanent hearing loss. Basically, your eardrums would blow out. So you definitely don't want to do that, okay? However, when you're talking about ordinary sounds like conversational sound and so on and so forth, the amount of energy that's present there is next to nothing. So let me give you an indication of that with the second of today's examples. Go ahead and copy that example down. Okay, I'm going to put it on here on the screen. And I'm going to go ahead and do a little bit of erasing. Okay, so just to give you an idea, that associated with ordinary sounds, the amount of energy that's present there is next to nothing. All right, so a person is 5 meters from a point source of sound. Sound waves reach the person with an intensity of 1 times 10 to the minus 6 watts per meter squared. That's 60 decibels, so that's fairly loud. So it's like you're blasting your stereo or something like that, and you're listening to it from 5 meters away. That's basically like right across the room. All right, so we've got R here as 5 meters for the distance. The intensity of the sound I is given to us as 1 times 10 to the minus 6 watts per meter squared. In part A of the problem, we're calculating the power output of the source. So this is in terms of the production of the sound wave. So here's the sound wave itself, and then right here is the power output associated with the source, P source, that we're asked to calculate. Here's the distance R. So then therefore, this is the first way in which we think of intensity I. This is equal to P source divided by 4 pi r squared. And now we just calculate P source, simple as that. All right, so P source then is 4 pi r squared multiplied by the intensity I, and we're going to end up here with a multiple of pi after I punch this out on my calculator. Let's see what we get. All right, so 4 times pi times 5 squared, which is 25, and then times 1 times 10 to the minus 6. And this comes out to be 3.14, as I said, it's a multiple of pi. 3.14 times 10 to the minus 4 watts. So the amount of energy per second that we're talking about here for a fairly loud sound at 60 decibels is still really low. It's next to nothing. So imagine that this right here is the speaker of a stereo, for example. You're listening to something that's rather loud and you're doing so from quite a distance away, say across the room. Yet even still, the power output of the source itself is next to nothing. It's in terms of 10 to the minus 4 watts. So let's say that you go to Best Buy, for example, and you're going to buy some stereo equipment. And then you look at the various ads that are there, and it says that the stereos are capable of pumping out like 300 watts or something like that. Well, most of the energy that you're buying there, quite frankly, is going into the actual electronics of the production of the sound wave itself. The amount of energy that's present there is next to nothing. Now, you're certainly never going to find any advertisements at Best Buy, for example, that advertise very loudly that the speaker output is going to be in terms of 10 to the minus 4 watts. You're probably not going to be impressed, but what you're actually seeing there is just a representation of all the electronics that are necessary to produce the sound. So just be aware of that. When somebody comes up to you in a blue shirt at Best Buy, some chipmunk, and he then says to you, check out this stereo equipment, it's capable of pumping out 300 watts, well, take that with a grain of salt. Okay? Okay, next part B. Let's talk about what happens with the reception of sound. Okay, so in terms of part B here for the sound reception, let's say you're standing at this distance and then we have a cross-sectional area A associated with your eardrum. That's 5 times 10 to the minus 5 meters squared. That's an accurate number, by the way. All right, so right here is your area associated with your eardrum. This is given to us as 5 times 10 to the minus 5 meters squared. How long would you have to sit there and continuously be exposed to the sound in order to receive just 1 joule of energy? 1 joule of energy is the amount of energy necessary for me to take the tape, for example, and raise it maybe a foot or so above the desk. That right there is basically 1 joule of energy, more or less. So just take a guess. How long would you have to sit here and listen to this continuously, a loud sound, such that you get 1 joule of energy through your ear? A couple of minutes, a couple of hours, what do you think? Well, let's go ahead and calculate. Okay, so now for part B of the problem, we'll think of the intensity I as P receive. How much energy per second is passing through your ear divided by the area of your ear. So let's go ahead and calculate P receive. This is just equal to I times A. So the intensity of the sound is the same as it was before. It's the same sound wave, 1 times 10 to the minus 6 watts per meter squared. And now I multiply that by the area of your ear. So times 5 times 10 to the minus 5. Like so, and this comes out to be 5 times 10 to the minus 11 watts. So notice how small that number is. This is the amount of energy per second that's passing through your ear. So then therefore, let's calculate the amount of time necessary for you to receive 1 joule of energy. Let's think of it now like this. P receive is equal to, we'll call it E receive, that's 1 joule, and then divided by the time t. And now what we're going to do is we're going to set the numerator here equal to 1 joule, and then just calculate the time. So to calculate the time, that's going to be E receive, 1 joule, divided by P receive. So it's basically just the inverse of this right here, and then I end up with an answer in terms of seconds. So what I do, this comes out to be 2 times 10 to the 10th seconds. That's 20 billion seconds. That's actually more than a human lifetime. It's considerably more than a human lifetime. If I go ahead and calculate the number of years associated with this, remember that there's about 31.5 million seconds in a year. This actually comes out to be almost 635 years. So because of the logarithmic nature associated with the decibel scale, when you're listening to ordinary sounds, even something rather loud at 60 decibels, the amount of energy that's present there is next to nothing. When you're getting upwards towards the threshold of pain and beyond, then yes, the energy is considerable, but when you're talking about ordinary sounds, the amount of energy associated with sound waves is not all that much, okay? Okay, that concludes here part 2 of the lecture. And that is, by the way, the end of today's lectures. Go ahead and continue working on the next problem set. I'll be posting that on Schoology very soon. Today's shirt is Amon Amarth. See ya. Be safe.